All right, good morning, everyone, and welcome to day 4 of Galaxy Evolution Week at Halo 21. Today we have Bryan as our keynote speaker, but I have some announcements first. Here's our image of the day. It's foggy today, and we'll have one more tomorrow. I think that's density, temperature, and metallicity. Yeah, and we actually have a couple new results this week. New results video, one from Stephanie Tonneson, related to work with our keynote speaker, and one with Sarah Appleby, with Romeo. And I recommend watching both. I actually haven't finished watching the second one, and I've been in communication with Sarah, so about other things. So I can't wait for that. Okay. I want to make an announcement, and this is something that us organizers have developed. Next week is a different format for Monday, and I think it's going to be a lot more interactive. Instead of speed collaboration for the second hour, we're going to talk about future observations. Of course, next week is Future Observations Week, and so we want your help in articulating and communicating the particular strengths and complementariness of different complementary observational approaches. Obviously, somebody else wrote this and improved this from my initial version, and I'm reading it for the first time. We got 7 inches of snow here, and I went for some 7-mile run in addition to shoveling. So, and I'm paying for it now.
Dang, we got 7 inches in Boulder.
Yep. Monday's second hour session will feature opt-in breakout rooms focusing on.
Just like, oh, I'm sorry, I just went skiing. I'm tired.
Okay. All right. Yeah. We should talk later, Matt. Yeah, you're in Carbondale. So Monday's second hour session will feature opt-in breakout rooms focusing on a diverse array of observational approaches, and each room's task will be to identify and describe what the observational approach will reveal about the CGM and report these strengths to the full group. So this exercise requires both experts and expert volunteers and eager participants. This is much better written than my first version. And please go to a new channel, Halo 21 OBS Domains, to signal willingness to be one of our expert volunteers. Just post your observational domain or domains so that people know that you will be joining the discussions. And we have initially identified these different observational domains, and they're pretty broad, and there's 9 of them. Absorption line studies, emission studies, X-ray, fast radio bursts, Sinaiv-Zeldovich, radio emission includes 21 centimeter CO, so a whole range, polarization, gravitational lensing, and just infrared. Infrared is its own domain. Without further ado, and after stumbling through a couple slides there, I am going to introduce our keynote speaker, Professor Bryan from Columbia. And I also want to highlight our panel that will take over in the second hour: Cameron Hummels, Dylan Nelson, Mary Putman, and Xijing Shen. So Greg, I will unshare my screen and let you share your screen.
So thank you. I'm really putting this talk together. I was really I had a lot of fun. I was asked to talk about how gaseous halos affect galaxy evolution, and I'll talk about in a moment my own spin on that. But I've subtitled this "The Circumgalactic Cathedral," in part because of the sort of almost religious experience that I've had over the last 6-7 weeks exploring the CGM with all of you. It's been an enormous privilege. I've learned a huge amount, and I have to give credit to our fearless leaders putting together this program. They've done, I think, a fabulous job. But also because I feel like it's sort of a bit fitting. The galaxy is surrounded by the circumgalactic medium, and one can make all sorts of connections between cathedrals. But finally, as you'll see, the center point of what I'm going to talk about is around an idea that Mark and I sketched out on my whiteboard probably 15 years ago, of a stained glass window, and so you'll see in more detail. But first of all, I want to be clear about how well I'm interpreting this question, and really, it's not just how gaseous phases affect galaxies, but vice versa as well. How galaxies affect their circumgalactic medium. So I'm going to divide this up sort of into two parts, although it'll actually be multiple components, but essentially looking at how the black hole affects its circumgalactic medium, and how the supernova feedback and the stars affect their circumgalactic medium. So I stole this. Thank you to Cameron Hummels for this beautiful image, and so I'm going to try and phrase this in terms of this diagram. So this is what I'm showing here is the cooling time as a function of the virial radius and halo mass. So we go from some Milky Way galaxies up to clusters on the right, and then down here to our lowest dwarf ultra-faint galaxies on the left. So this sort of spans the observable galactic systems, and we go from a radius of something little 0.1 RVIR out to the virial radius. And of course, that's all quite arbitrary. But the point is to sketch out, and this cooling time is computed assuming that the profile looks a lot like an NFW profile with the density suppressed by the baryon fraction. So that's one possible model. One can, but the broad picture is not debatable. There's these regions where the cooling time is very long, and these regions where the cooling time is very short. And that's going to influence how the circumgalactic medium interacts with the galaxy at the center. So I'm going to take this diagram and I'm going to split it into panes. So what I'm calling this the circumgalactic medium stained glass window. So I'm going to start off with this phase, this region, this pane over here, which I call the long cool. And this is the region for which the cooling time is long compared to the Hubble time. So these are systems for which the gas falls in, hits the accretion shock at the outer, around the virial radius, and the entropy is enhanced and simply doesn't cool. And so this is the simplest connection to the host galaxy. There is no connection to the host galaxy. This is a plot showing the entropy profile for a set of AMR clusters, SPH clusters, along with a fitting formula, which shows roughly the entropy going as radius to the 1 power. So, and so I show this because there's a lot of consensus. This is the community. I think the simulation community has reproduced this particular result many times. And indeed, if it can compare it to observations, so the intracluster medium, of course, or the circumgalactic medium of clusters, as I prefer to call it, can actually be imaged out to large radius. And so there's been a number of attempts to do that. Here is one showing reasonable agreement with the X-ray observations. So this gives us some confidence that our overall picture of how gas inflow, at least for large masses, is correct. But obviously, it's not that. The connection is not very strong. So let's turn to the next pane of this window, which I simply call the AGN regulation pane. We can come up with better names later. And you notice, so it goes down to about 10 to the 12 solar masses. I've tried to make that a little fuzzy because I'm not exactly sure where that boundary is. But then I have this little cutout down here, which I'll come back to in a little bit. But I want to spend some time talking about this, but not too much time, because this has been covered a number of tutorials, which I'll point out later. So I take this nice plot. Actually, Mark put it together, but the data points come from paper by Massimo Gaspari and collaborators, and it shows the black hole mass as a function of the temperature, the virial temperature or the measured temperature of a set of clusters, well, down to groups and ellipticals as well. And it shows this very tight correlation. This is actually maybe one of the tightest correlations for the black hole galaxy connection. It shows that it falls along this line. If you take the black hole mass and you convert it to an available amount of energy, then you can compare it to the energy available from supernova, which are given here, depending on how much. So this just takes the halo mass, converts it to a stellar mass, and then depending on how much energy is available, these curves match here. So one point this makes quite clearly is that supernova feedback alone is not sufficient to change the properties of the circumgalactic medium. We need AGM. But it also shows that there is this very tight correlation, because the other thing which is shown here is this dashed blue line, which is just the energy of the circumgalactic medium itself. And you see there's this nice correlation indicating that the black holes are on a very deep level. The energy input is deeply connected to the energy content of the circumgalactic medium, so implying regulation. So what is the form of that regulation? So one idea that's had a lot of talk is this idea of precipitation. I don't want to go into a lot of detail about this. This originally, this idea in various forms is quite old, but there's this beautiful paper by Mike McCourt and Prashad and Elliot Quartet, demonstrating that in a medium with thermal equilibrium, that it's unstable to precipitation if this ratio of this cooling time to freefall time is below some critical factor. So a number of groups have connected that idea to accretion onto supermassive black holes, and the idea being that when precipitation occurs, the gas falls and condenses out, cools, condenses out, falls into the black hole, drives some bipolar outflows with high specific energy, which heat the CGM and return it to a state. So I can't resist showing this. Yuan Li did the simulation and produced this movie and set it to sound as well. I don't know if it actually comes through or not, but anyway, you can see the condensation which is occurring, and sometimes it turns off, and there's a supermassive black hole right at the center. This is about 80 kiloparsecs, and you can see that this system does indeed balance heating and cooling. In fact, you can show that more rigorously. So there's a fair amount of evidence that this is actually occurring in nature. So here's some results showing a set of clusters observed of clusters showing the ratio of their cooling time to freefall time. These are the ones which have evidence for cold condensing gas, and these are ones which don't. So this condensation, this precipitation mechanism seems to be operating. And so what is its prediction? The prediction is that therefore the circumgalactic medium should be in this critically precipitating state. Of course, this might be episodic. There might be outflows which heat the gas, and then the gas returns maybe even to a cooling flow state for a brief period of time. And then the heating begins again. But in general, it makes this prediction that the gas density should be lower. So this is a plot of again, actually taken by, you'll see Mark's work features quite prominently in a number of places in this. So this line is the prediction, just the NFW prediction, and then the black line here is the critical precipitation prediction. And so it nicely matches the observations. And the other point you can see is that it decreases, the amount of mass in the system decreases as you go to lower mass systems, because their precipitation requirement implies lower densities, and therefore they require the black hole to heat them up and keep them in this state. So this is I think nicely being found also in cosmological simulations. So I won't go into a lot of details, because this was covered I thought very nicely by John Davis's tutorial presentation yesterday, in which he showed the very same plots. Which just shows for Eagle and Illustris, and I want to focus at the high mass end here for now, showing that first of all that there is this decrease, and in fact this decrease is simple to understand. It just comes, if in the precipitation picture anyway, it just comes from the idea that, well, actually even more generally, comes from the idea that as you go down in mass, more of the gas is at a cooling time less than the age of the cluster, and therefore it has to either be heated or condense out and cool. So you can make very simple predictions for this relationship, just based on atomic physics plus cosmology, which produces curves which look much like this. But this, of course, goes on to show more than that. It shows that there's this correlation with, it shows that it is in fact the black hole which is responsible for this, because it shows this correlation between the black hole excess mass, excess black hole mass, and the properties of the circumgalactic medium. So this is, and one can go beyond that and look at the correlation between the black hole mass and between the circumgalactic medium, but also the star formation properties. So halos which have less gas tend to have lower specific star formation. So this is a quenching mechanism, and it directly connects the properties of the circumgalactic medium and also even the morphology of the rotation of the disk. So as I said, I urge you to watch John's description of those results in more detail. So the TNG collaboration has also looked at this question. So this is a paper by Zinger et al. That Annalisa has mentioned, and it looks at this focus on the right-hand side here, which goes across the stellar mass. So and up here is the corresponding halo mass, and it shows that that as we move up here, the entropy of the gas increases. And that's because, again, because this this gas has to would otherwise have cooled and accreted onto the black hole and been heated up. But also it shows this correlation with the black hole mass and the kinetic to thermal energy mode of the black hole feedback. So this is showing that this is a nice demonstration of the preventive aspect of this feedback. There is also some interesting. There's this interesting paper by Erica Nelson showing some evidence for an ejective component as well. It would be one of the interesting questions is what is the importance of these two kinds of mechanisms? The black hole either ejects the gas in the disk to quench, or it heats up the circumgalactic medium and prevents its infall. So these two different modes are quite interesting to look at. With a graduate student at Columbia, Bryan looked at this recently with AMR calculation, exploring different modes of accretion. So one in which the accretion onto the black hole is dominated by torques, and another where it's driven just by the traditional Bondi-Hoyle prescription. What we found is that in both cases there were some interesting differences, but the preventive nature in both cases was the primary driver for the suppression of gas inflow. So this shows the decrease in the amount of gas which was flowing in from redshift 1 to 0. So this is how much the inflow decreased versus how much the outflow increased. So in fact, mostly, so this is a sign of ejective feedback, massive outflows driven by the supermassive black hole, where this is a sign of preventive feedback, mostly gas preventing from being flowing in. So one of the key questions I think which we still don't know is how does this AGN heating actually occur? So Dylan Nelson went through, I thought, a very nice job of talking about the various numerical algorithms, or physical algorithms, which are used in various simulations to eject energy into the galaxy, into the circumgalactic medium or the galaxy. I think so in particular, how much of this is this a jet? Is it a wind? How does the heating actually occur? Is it shock heating? Is it mixing of hot bubbles? Here I think we don't know the answer to this. I'm just throwing this up. This is Kang-Yi Su, some recent work by Kang-Yi, exploring many different models. You have to read his paper to actually be able to read this. He did simulations of many different models within the fire context, but these are all idealized 10 to the 14 solar mass halos. And one of including some cosmic ray feedback, which was quite actually successful in quenching. But one of the interesting things that came out of this is that the width of this cocoon, so generically the jet drives, of course, this bipolar outflow and produces a shocked cocoon, which can, depending on the energy density, the mass loading of the AGN jet, can either be quite elongated or quite round. And so what Kang-Yi found is that in order to get suppressed cooling, it needed to be relatively round. That if this jet was too much like a drill, then the energy was deposited too far out, and cooling was not successful. Of course, this may vary depending on different mass halos, so that's a natural next step to look. lots of other people have looked at the impact of AGN jets, and I think, including Yuan Li, who looked at this and found it was primarily shock heating, which did many weak shocks of this cocoon passing out, which did the bulk of the heating. But turbulence, mixing, cosmic rays are also all potential energy sources. I think this is a question we don't have the final answer to yet. Okay, so that was AGN regulation. Next, I want to fill in this little gap down here, which is where type 1a supernova heating can be important. So I want to look, briefly summarize one particular model for this type 1a supernova heating. But I want to just point out in general that there's been some nice work. Daniel Wang did some early work looking at this point because there's this range of masses for which type 1a supernova heating can be important, right around 10 to the 13 solar masses. For halos, galaxies at low masses, there's just not enough population of old stars. And for halos of higher mass, the potential well is too deep for this to have an important effect. So type 1a supernova, this is an estimate of if you take a population which is about 10 billion years old, and you take the energy input from that and you divide it by the mass loss from stellar winds and other products, then you get a specific energy of about which is comparable to the specific energy of the CGM in this range. And so this particular model that so Mark has put out just recently, so actually I'm going to move through this quite quickly in Halo 21 quenching, which he goes through this in considerably more detail. But very quickly, the point is that of course, one crucial point is just this balance. But if you take the CGM entropy profile as some power law with radius, then and require it to be in equilibrium with a wind, then the resulting entropy profile has a form which can be written in this like this, and so for which becomes steeper as the circular velocity increases. So that makes sense. At low circular velocity, when the potential well is narrow, the specific energy dominates and the wind just flows out. Whereas as it steepens, it has to do more work. As the potential well deepens, it has to do more work, and so the entropy profile steepens. So there's a critical profile such that this balance occurs, and also that happens to be also the critical profile for which the cooling time to free fall time ratio is a constant. So that makes this interesting regime right around. This power law of 2/3 occurs right around a mass of about 10 to the 13, or a circular velocity of 330 kilometers per second, or a velocity dispersion of about 240 kilometers per second. So the idea in a nutshell, if we is that right around this critical point of about 240 kilometers per second, where the curves, the profiles are all critical or somewhat above that, then we have this we have this two phase kind of if the outer CGM pressure is low, then the solution is allowed such that the cooling balances heating, and this wind is stable. However, that deposits mass at large radius, or there can be accretion, and that drives up the outer pressure. And so eventually that outer pressure's boundary condition is high enough here that this profile no longer can balance. And then the gas accretes onto the black hole at the center and heats up the CGM, which then the outer CGM, the jet, assuming it's a narrow thin jet, gets out, heats up the CGM, decreases that mass, the density out there, decreases the pressure, and you return back to the state. So this is a cyclical process in which the black hole operates as a valve, and the type 1a supernova either effectively stably sweep out the material or they don't. And this operates most effectively at higher mass and above. So this I'm focusing just here on this picture on the right for this critical velocity dispersion and above, and this just is a depiction of this idea that this outer CGM is heated by periodic AGN jets, and they're controlled by this type 1a sweeping energy wind, type 1a driven wind. So there's other possible ways in which, of course, in which the type 1a heating can play a role. But I want to get into this fourth pane, what I call the core collapse supernova regulation phase region. So down at masses below 10 to the 12 solar masses or so, and where the energy input for the CGM has to come from supernova. Well, or at least can come from supernova. There may be an AGN contribution as well, but I'll assume that's minor. Of course, as has been noted a few times before, for halos at this mass and below, the shock, the cooling time is very short. Emphasized in the first diagram showing the cooling times, and therefore Birnbaum and Deckel showed that the shock actually, in the spherical case, doesn't even form, that it's unstable below this crucial mass, and this and in the absence of any feedback, then the gas flows in and is largely cold. And Dushan did a nice job of talking about all of the recent results on cold filamentary flows. So I want to focus instead on this the regulation part, the regulation of the CGM, and so I want to highlight here a pair of simulations done by Drummond Fielding a few years ago, which looked at a halo mass here. These are two different simulations. Time goes down from top to the bottom. They're both for 10 to the 11 solar mass halos. On the only difference here is the mass loading of the wind. So here on the left, the mass loading is high. There's a ratio of 5 for the wind ejection to the star formation rate. And just to be clear, these are simulations which essentially cut out the very center. So there's no attempt to model the galaxy itself. Any gas which accretes onto the center is ejected back with a certain amount of mass, a certain amount of energy, and a certain loading factor. So so if the loading factor is quite high, then these winds are baryon dominated and so cool rapidly. So you can see an outflow here, which is quite cold. And then in the end, essentially what you get is a set of cold clouds which are moving almost ballistically, and there's no clear formation of a shocked hot halo. On the other hand, if the mass loading factor is low, so the specific energy of the outflows is high, then you can produce a shock and a hotter gas. Now, in this case, I mean, so on the left here, I show that Drummond shows the shock radius as a function of the virial radius, and so you can see that this plays a key role in whether a hot halo is set up. Now, to be clear, even in this case on the right, he didn't find much evidence for this kind of precipitation picture that we talked about. The flow here is still very chaotic, and the pressure support is significant, as Cassie Lockhouse showed by analyzing the same simulations later, is dominated by turbulent motions of the gas and not by the thermal pressure. Although I think this is still an open question. The energy of these winds is still not that high. The specific energy, there's more specific energy which could be injected, which is available from the supernova. So, but the point here is that it shows a key question. If we want to understand the properties of the circumgalactic medium in these low mass objects, then we need to be able to answer this question. So, are the outflows high in specific energy or low mass loading, or vice versa? And this turns out to be a critical question because, as I just showed, it determines what is the thermodynamic properties of the circumgalactic medium. And Dylan, I thought, also did a beautiful job of talking about, particularly within the context of the TNG work, of the outflows, properties of the outflows in those simulations. So I want to actually focus on something, try to answer this question in a slightly different way, which is to focus down on even smaller scale simulations. The problem with cosmological simulations, of course, is that they can't resolve the individual supernova set-off Taylor blast waves, and so have to make some sort of approximation for understanding the feedback from all of these supernova explosions. So this is, I'll just set it going, is Chang-Gu Kim's beautiful Tigris simulation results, in which they can resolve this and can see the driving of individual outflows. So this is shows many different properties. What I want to focus on is the temperature of this gas. There's a lot of hot gas which is flowing out. Notice it's the hot component which has the high outflow velocities, and the colder component has generally actually inflow. So these are very useful to understand the outflows. Of course, the weakness here is that they don't go beyond a few kiloparsecs, and they also don't have the global geometry. So diving into those simulations into a little bit more detail. So here's one. This is set up to mimic the Milky Way at about a 4 kiloparsec, so somewhat more star forming than our local region. And this shows the outflows as a function of time. Sorry, I clipped the time axis here. But this is of order a gigayear. So this is the red shows the outflow of the cold component, and you can see it's undergoing a galactic fountain. It flows out, it gets to about a kiloparsec or so, and then comes back down. On the other hand, the hot component flows out and escapes. In fact, it leaves it at more than the escape velocity. And this just shows that, so this paper, Chengu's paper, has many beautiful results looking at a wide range of different box conditions. And here's one that I just pulled out, which just shows the mass loading factor of the cold gas, the intermediate temperature gas, and the hot gas. And you can see that one of the interesting results is that the mass loading factor of these calculations is actually quite low, and it is decreasing with height. So now, so it's dropping below 0.1 in these cases. On the other hand, the energy, if I were to show a similar plot for the energy loading factor, it's dominated by the hot. In fact, I'll show results which later, and is constant. So this is an interesting result. Evan Schneider, so this beautiful 3D image I won't show, that's been shown before from the Seagal's calculation, which has similar high resolution, but has the geometry of the full system, and this produces a similar result. The outflow, mass outflow, is dominated by the hot component, and as is the energy, and the mass outflow in the cold component is dropping at larger radius. So these are high specific energy outflows. There is a cold component, definitely very interesting, but in detail, it seems to be getting entrained at small radius, transported outwards, and then mixed back into the hot medium at large radius. So this is telling us something about the basic dynamics of the outflows. Miao Li collected together a set of results from a wide range of these tall box calculations. Many workers using many different codes, AMR codes, fixed grid codes, SPH codes, and found as long as you had very high resolution, this basic outflow result seemed to hold, that most of the energy came out in the form of the hot and not the cold. In fact, Dylan, I think, showed very similar results for TNG. And these match the this seemed to match the X-ray properties observed in some of these outflows. In fact, the things like M82 seem to show very high energy thermalization efficiencies and are producing very high specific energy outflows. I won't go into a lot of detail about this, but the hot outflows also carry metals. So here's again this compilation from Miao's paper, which shows the correlation between the energy loading factor and the metal loading factor. So that's again an indication that these outflows are really coming straight from the supernovas. Okay, so given all that, what can we say about the CGM-Galaxy connection? Well, we don't have an answer. I've given you some reason to think that the outflows may be high specific energy, but I think we don't yet know. Those simulations I showed you before don't cover the full parameter space that's required to understand this. So we can have a few different ways of thinking about this. One is that the CGM is heated up, is largely hot, not to say that there's not cold phase. In fact, in a hot pressure supported medium, we naturally arrive back to this gas precipitation picture I talked about before. Another possibility, though, is that the loading factors of the winds are high, and the CGM, especially as we get to these lower mass halos, is relatively cold, is in fact supported by some sort of turbulent lake process, and the clouds are really juggled or ejected rather than in some sort of equilibrium state, in which case what's really important here, these two processes are quite interesting because in A, the crucial thing is the cooling, which controls the structure and the accretion and hence the star formation, whereas in B, it's really the physics of the winds which control the CGM properties. And then finally, I really unfortunately don't have time to go into the cosmic rays, but there's been lots of nice work by a wide variety of groups looking at this. And in this case, the cosmic the CGM is in the extreme case in which it's cosmic ray pressure supported. It can be cold in regions, but still pressure supported. So I think a nice simple picture explaining this picture is sort of this situation is still needs to be worked on. So I will say, if it is in fact precipitation and regulated by supernova, then there is this nice prediction, simple model that Mark put together a few years back, in which if you just take the simple idea that this requirement of the precipitation requirement applies to low density halos, then remarkably, because the cooling rate is the CGM mass divided by the cooling time, and the CGM mass depends on the cooling time, then the accretion rate ends up being inversely proportional to the cooling rate. And so paradoxically, the faster the cooling, so the more effective the cooling, the less mass there is to cool, and so the less star formation you get. And so this is a comparison between a compilation of galaxy mass fractions versus this prediction, assuming the precipitation picture holds. Okay, so to better understand the flow of mass from the galaxy, and the flow of mass, momentum, and energy from the galaxy into the circumgalactic medium, it's useful to actually go into the simulations to measure these things. So Dylan talked about some of this. This is an upcoming paper by Viraj Pandya, who is looking at the fire simulations and trying to characterize all of these loading factors in two places. One, out of the galaxy, so out of the ISM and into the CGM, and two, into and out of the CGM from the circumgalactic medium. So I'm going to focus first of all mostly on this region, the outflows between the galaxy and the circumgalactic medium. So I'll just quickly show this movie, which is one of the fire halos. This is a 10 to the 12 solar mass fire halo. You're seeing this outer line is the virial radius, and this is a zoomed in region in which you see the outflows and the inflows. And mostly what I want to point out here is that many of the outflows are hot, but not all of them in fire. Some of the outflows are actually cold, and this characterizes that. This is a phase diagram of the outflowing material, and you can see much of it is hot, but there is a component which is going out cold. And then this is correlating it with the star formation rate, and this is a radial view of the inflow and the outflow. So there's lots of interesting results from this. I want to pull out two things. One is that is just a characterization of the mass loading factor in the fire simulations. As a function of the stellar mass, as others have pointed out. I think Moratov analyzed a similar set of simulations. This work tries to do an improved job by removing gas that is not going to make it out to the circumgalactic medium by doing a cut on the Bernoulli parameter. But for the mass loading factor, the results are quite similar, and the mass is carried partially in the hot phase, for the high mass halos, almost all in the hot phase. For low mass halos, it's low in the warmer phase. But keep in mind that the virial temperature of these guys down here is actually close to 10 to the 5. So part of this is just the fact that these flows are at the virial temperature, as I'll show you in a little bit. And then the other thing, so one can also look at momentum and metals, but the thing I want to pull out here is the energy loading factor, which shows how much energy is actually getting out of the halo into the circumgalactic medium. And this depends on redshift and on halo mass. But generally, interesting enough, at higher redshift, when the outflows are burstier and at lower masses, the energy flowing out is higher and is comparable to the energy available in the supernova winds in some cases, at least at early times. And as promised, this energy is carried largely by this hot phase. Finally, I want to turn to the lowest mass halo. So I'm almost out of time, which is good because I'm almost out of things to talk about here. These very low mass halos, which have very low temperatures, and I can't resist throwing this in. If you go to the very lowest mass halos that one can imagine forming stars, population 3 objects, they also have a circumgalactic medium. This is a calculation of a 10 to the 6 solar mass halo at redshift 20. So one has to make a redshift adjustment so it has a virial temperature less of a few thousand degrees. And what you see is that it actually has a nice circumgalactic medium. This is a zoom in. Here is this hot medium. And the center is cooling. So here's the thing. This is a zoom in 6 parsecs and then even smaller. And what's interesting here is that this really does form a classic cooling flow. So as Jonathan Stern has developed some nice models, this really is just flowing in. The compression time is equal to the free fall time, and the gas is actually thermally stable, and so this is a classic cooling flow situation. So for once you introduce metals, then things of course get more complicated, and you go to slightly higher mass. Then feedback again becomes important. I just want to highlight this work in this context. One thing that came out of this work that Viraj led. So this is another paper which came out recently, comparing the fire calculations to semi-analytic models. And again, there's lots of interesting results. But the key one I want to point out is that for the 10 to the 12 solar mass halos, both the semi-analytic model and fire predicted similar CGM masses, but the SAM underpredicted drastically. So this is Rachel Somerville's semi-analytic model. It drastically underpredicted the amount of circumgalactic medium, and this was interesting because what it was doing is it was just using these very short cooling times and assuming that the gas had to cool very rapidly under the galaxy, and therefore required very strong ejection out. But the other thing that was happening is that the fire simulations predicted much lower mass inflow rates at the virial radius. So you remember I drew those two circles, one the ISM at 0.1 virial radius, but the other out at the virial radius. And this shows the mass inflow rate as a function of time for these various different halos. So the red is the high mass halos, but I want to focus here on the low mass halos, the 10 to the 12 ones. The fire inflow rates were down by a factor of 10 from the simple prediction that the baryon inflow rate at the virial radius is the baryon fraction times the dark matter accretion rate, which is what semi-analytic models almost always take. And so this required the SAM to work extra hard in these low mass halos to inject a lot of mass. So one thing maybe in the interest of time, actually I'll skip over this and just show you the movie. So this is the same thing I showed before, but now for a 10 to the 10 solar mass halo. And what you can see is that these guys produce shocks which go way out beyond the virial radius, and they heat gas many times the virial radius, and so they really completely control their own surroundings. That means that they set their own inflow rate, which is much lower than what you would naively predict. So these produce so this outflow for these low mass halos really changes the properties of the intergalactic medium well beyond the virial radius, and that causes the inflow rate to drop substantially. And actually, so these are just some simulations done by an undergrad at Columbia, and I just wanted to emphasize that for halos of around 10 to the 10 solar masses, we're finding that the temperatures of the circumgalactic medium are actually around the virial temperature, even though the virial temperature is about 100,000 degrees, so not too far from the peak of the cooling curve. And so the density is much lower, but the cooling time is still quite long for these systems. What is controlling the CGM properties in these very low mass halos? Well, in the inner regions, actually it may be precipitation. We've got gas around this critical factor of 10, but in the outer CGM, it's clearly not. At least not in these simulations. Something else is keeping this gas rather than it's not at the critical precipitation balance. So there's lots of interesting possibilities. Photoionization, cloud density contrast is low. I'm going to completely skip angular momentum because Crystal Martin did such a great job of that. And I'm going to completely skip satellites because Annalisa did a fabulous job of that on Wednesday. So thank you to both of them for making my job a lot easier. And I'm just going to stop and leave you with, rather than summaries, questions. So, and they primarily have to do with how exactly the outflowing material from AGN or supernova-driven winds interacts with the circumgalactic medium, and what is the process which really sets this connection? Is there some simple, like precipitation, some simple model which controls the structure, or is it something? Is it just simply that the outflows are throwing out a lot of mass? So thank you, and I'll stop there.
Okay, thank you, Greg. That was a very comprehensive keynote, and I like those questions at the end. I took a screenshot. In fact, we are going to take we'll take come back at 9:12. We need about a 6 or 7 minute break. And I encourage everyone to go to Halo 21 Week 7 Evolution to not just ask questions, we got a few there, but also to vote on them and see what you would like to discuss. So we'll see you back here in about 6 minutes.